three pictures, I think, are really impressive. You look at the relative error going down. This is percent, okay? So the relative error in the 40th eigenvalue, well, that's already enormous. But the relative error, say, in the 10th eigenvalue is 0.0013. Okay, that's really impressive. That's down on, at the order of, 1/1000, one part in 1,000. That's really accurate. And when you look at modes like this is the n equals 1 mode. Remember, this is supposed to be valid in the limit as n goes to infinity, right? So n equals 1 is pretty close to infinity here. Okay, and it only gets better from here because here's n equals 2, and now it just looks like your pencil has gotten a little bit thicker in places. Okay, so WKB is really terrific. And remember what the conclusion was. The conclusion is that the eigenvalues En, the eigenvalues, are growing like a constant times n squared. And this is, we just showed that this is true for all Sturm-Liouville problems. Okay? All Sturm-Liouville problems, the eigenvalues grow like n squared. Can you think of a quantum mechanical problem where the eigenvalues grow like n squared? The nth eigenvalue is a constant times n squared? Very good. An infinite, what kind of well? A square well. Yeah, an infinite square well. That's right. And that's because that's the problem that we just solved. And in fact, for the infinite square well, WKB isn't just an approximate answer. It gives you the exact answer. Okay, it's the exact answer. But it isn't true for other eigenvalue problems that the eigenvalues grow like n squared. Can anybody give me an example where the eigenvalues for large n are not asymptotic to a constant times n squared? Say it again? Hydrogen atom, indeed. In fact, there, the eigenvalues are going like 1 over n. Yeah, that's strange. The harmonic oscillator. How do the eigenvalues grow with the harmonic oscillator? Like n. Okay? They grow like n. So, and in fact, the eigenvalues can grow like some interesting fractional power of n. And that is what happens in the anharmonic oscillator. And you're going to see that. Okay, so in the x to the 4 oscillator, not the x to the 2 oscillator, the x to the 4, they do not grow like a simple power of n. Why in quantum mechanics do we not have this universal n squared behavior? The reason is that it's not a regular Sturm-Liouville eigenvalue problem. It's a singular Sturm-Liouville eigenvalue problem. And that's because the problem is posed on the infinite line and not on a finite region. Okay? So let me explain to you the problem that we are going to solve today. This is a real tour de force. It actually doesn't take that long to explain it, but it is an amazing collection of arguments. It's really absolutely beautiful. And you now know, I think you know from what we've said in the class, enough to follow every step in the argument. Okay, we have covered all of the bits that you need to follow this argument. So the problem that we're going to look at is the problem of finding the energy levels in a potential well. This is the standard eigenvalue problem. So we have a differential equation, a Schrodinger equation. Okay, that is the Schrodinger equation. But now we're going to pose this equation on the infinite line, not on a finite region as we did with this stuff here, but on the whole line. And so the problem is going to be psi of plus infinity, or let's say just say psi of x goes to 0 as x goes to plus infinity, psi of x goes to 0 as x goes to minus infinity, okay? And v of x is called the potential, and v of x looks like this. Let's some potential like this. Okay, so this is v of x, and this is x. And we want to know what are the possible energies of a particle confined to this potential well. Okay, so this is the energy axis. Okay, so I'm plotting the potential energy on that axis. I'm also plotting E. Here's E, the energy of the particle on that axis. And what you know is this. If the particle, let's say, is over here, suppose this is the particle at the point x, it has this much potential energy, let's say potential energy, and it has this much kinetic energy, okay? And what quantum mechanics says is that a particle confined to a potential well, a classical particle confined to a potential well, if it's restricted to the real axis, because we had some interesting stuff to say about that yesterday, but if the particle is constrained to the real axis, all it does is go back and forth in this potential well. It isn't really going back and forth, it's really going around and around. Okay, but never mind. It's constrained to this potential well, bounces back and forth, and the particle can have any energy you would like it to have. But in quantum mechanics, it can only have a discrete set of energies, and we are looking for this discrete set of energies, E. That's the problem. Okay? Now, how do we solve a problem like this? Well, to solve this problem, this is an arbitrary function, v of x. It's arbitrary except for the fact that we want the function, let's say, to rise at infinity like this. To solve the problem is impossible. To solve it exactly is absolutely impossible. Nobody knows how to solve a differential equation like that. So we're going to introduce an epsilon, and in fact, we're going to call it epsilon squared just to keep things simple. And we're going to solve, and we're going to say, let v of x minus e, we're going to call that q, just for simplicity. Okay? And we're going to solve the following problem. Epsilon squared psi prime prime is equal to q of x times psi. Okay? And we're going to assume that epsilon is small compared with 1. And we're going to use WKB to solve this problem, and we're going to have a problem solving this problem. Why is that? Or in fact, we're going to have two problems solving this problem. Why are we going to have a problem? Because we are going to use the physical optics WKB approximation. Okay? And we know that the physical optics WKB approximation breaks down if Q is 0. Okay? Can't possibly be valid. And Q of x is equal to 0 in two places. Okay? Q of x is equal to 0, remember, when V equals E. That's a turning point. That's when the particle has no kinetic energy left. And there's one such, great. We haven't made pictures with colored chalk. Let's make color. Okay. There is a turning point right there. Okay. And that's the place where V is equal to E. And So at this point right here, and at this value of x, right there, WKB is not going to be valid. Okay? So this is called a two-turning point problem. Okay? Now the question is, how do you solve a two-turning point problem? This is really a challenge. Okay? And to start with the analysis, what I propose to solve is the one-turning point problem, because you can't jump from 0 to 2. So yesterday we solved a no-turning point problem, and that's because we made the assumption that Q was never equal to 0. Okay, remember yesterday we made that assumption. Q was positive because we had a regular Sturm-Liouville eigenvalue problem. So now, what we're going to start out doing today, you're going to find, by the way, that going from a one-turning point problem to a two-turning point problem is easy. But going from a no-turning point problem to a one-turning point problem is not so easy. That's an interesting challenge. So we're going to solve the one turning point problem. And let me pose this problem very carefully. Okay? The one turning point problem, if you like, focus just on this much of this picture. Okay? If you just look at this part of this picture, right in the middle of the picture is a turning point. Right there. Okay? So let's forget the fact that, whoops, there's another turning point over here. Just let's simplify things. Just forget that fact. And I would like to solve the following problem. Let's solve epsilon squared y prime prime equals q of x times y. And these are the conditions of the problem. Q of x equals 0 for just one value of x. Okay, there's only one root, one real value of x. And for simplicity, why not put it at 0? Okay? So just for fun, let's assume that which is x equals 0. Okay? So we're assuming that q of 0 is equal to 0. And in fact, if I make a plot of q, I'm going to assume that q looks like this. So q is some function. It only passes through 0 once, and it comes along like this. It passes through 0, and it goes on like that. So I'm assuming that q is positive over here, and q is negative over here, and it never gets to cross the this x-axis here. This is q of x. It only crosses once, never gets to cross another time. So it remains positive over here, negative over here, and it's 0 over here. But we have to make some assumption about how it crosses 0. There are a lot of functions that pass through 0, okay, and they can pass through 0 in different ways. And I'm going to assume, in this class, I'm going to assume that q of x passes through 0 linearly, okay? That near 0, this is a straight line right there, okay, approximately a straight line. So I'm going to assume that q of x looks like ax as x goes to 0, just passing through 0 linearly. And I'm assuming that a is a positive number. That is, the slope at 0 is positive. Okay, if a were a negative number, then this picture would look like this. Okay, it would be going down rather than up. Okay, now, this is what I'm assuming about q. We need to say something about boundary conditions. And you remember that I gave you a harangue about, hang on just a sec. Remember I gave you a harangue about how physics is all about subdominant solutions, okay? Nothing blows up at infinity, okay? Now, if q is positive, the solution has a different character than if Q is negative. Now, can you tell me what is the character of the solution if Q is positive, and what is the character of the solution if Q is negative? That's right. If Q is negative, this is going to be oscillating, right? If Q is positive, it's going to be exponentially growing or decaying. How do we know that? Because we know WKB. Okay, we just look at the WKB solution. And that means that in this region, okay, in this region here, the solution is going to be oscillatory. In this region here, it's going to be growing or decaying exponentially. We do not want it to grow. We're interested in physics, so I'm going to impose the condition that y of plus infinity is 0. Okay, now you had there was a question. Yeah. Oh, we don't need to assume Q is monotonic. Oh, no, we don't care whether Q can be monotonic or not monotonic. When I drew it here, I specifically, we could have wiggles that look like this. Okay, Q does not have to be monotonic. But the one assumption we are making is that Q is equal to 0 only once. Okay, but once it passes 0, it could go up and down. It could do anything it likes. Yeah.
Why do we assume that in some Q is negative and in other regions is positive? Why don't we assume that Q is always negative and always positive?
You mean this? Are you talking about this curve? Why am I assuming that? Because I want it to pass through 0. I want it to have one turning point. Oh, you're saying, why don't we have something like this? We could do that. And in that case, near this point at 0, let's suppose this is, or let's put this at the origin. Okay, we can translate it to the origin. In this case, Q of x looks like ax squared. And that's a whole new problem.
That's homework.
And that's what you're going to do for homework. Okay, but you could also assume that Q goes like ax cubed. Okay, however, the most likely possibility, if you expand Q in a Taylor series, is that it has a non-zero linear term. We know that Q, the first term in the Taylor series, is 0. And the most likely probability is that it has a linear term. What you would like to assume is that it also doesn't have a linear term, and that's a very interesting problem. You're going to solve that problem. Okay, and the techniques will be essentially the same as what we're doing today. So if you listen today, the homework will be routine. If you don't listen, it's going to be very hard homework. Okay, so but you understand why I'm assuming it's linear. Remember, we said this is the formula for Q. Okay, so let's just Taylor expand this. Okay, if you just do a Taylor series expansion of Q, then Q of x, the first term, if it vanishes, let's call this point, alpha over here, something like that. Then if you Taylor expand this, the first term will be Q of alpha, and the next term will be Q prime evaluated at alpha, but Q prime would be V prime of alpha, because the derivative of E is 0, right? V prime of alpha times x minus alpha. Okay, and the next term would be V double prime of alpha over 2 factorial times x minus alpha squared, and so on, okay? And of course, we know that Q of alpha is equal to 0 by definition because it's a turning point. It vanishes. But there's no reason why V prime of alpha should be 0. No particular reason. Why should it be 0? But it could be 0, and that would be very interesting. Okay. But the most likely thing is that this is some random number, 48, something. Who knows? Okay? And that's what I'm assuming is A. That's the derivative.
V prime at some point outside zero just means that the velocity around this point is v.
That what?
Because we know that the force in this point is the derivative of the potential.
Yeah.
So the potential, the force at this point is v.
No. No. It's the derivative of the potential. The force is not zero. The force will be this way. The force will be negative because the derivative of the potential here is positive, and the force will push you back toward the center of the well.
No, I think at some point v prime is zero.
Oh, if v prime is zero. Ah, yeah, that's right. That's an interesting problem. That's right. If v prime happens to be zero. That's right. Oh, we can talk about that later. Okay. So these are the assumptions I'm making. This is the one turning point problem. Now the question is, how are we going to solve this problem? And what is the problem with the problem? And why is this difficult? Well, you know where we start. We start by writing down the WKB approximation. Okay? So let's assume that x here is not equal to 0. Okay? What's the WKB approximation? Well, WKB theory says, and in fact, let's go into the region over here. Let's just consider this region. So let's assume that x is greater than 0, just greater than 0. What does WKB say? It says that y is asymptotic to some constant, okay, let's call it c, times e to the plus or minus integral up to x dt square root of q of t divided by q to the 1/4 of t. That's what the WKB, times 1 over epsilon. And this is asymptotic as epsilon goes to 0. And that's what the WKB approximation says. And what's wrong with the WKB is that it predicts that y blows up. This is x here. That y blows up as x goes to 0 because q is 0. And that's simply not true. Y does not blow up. Okay? That's the problem with the WKB. So we have to assume that x is greater than 0, but x cannot be 0. Okay? So what are we going to do about 0? That's the problem. Now, this is the region here, all the way out to infinity. This is the region that we're talking about right now. And let's call this, we can play with the colored chalk today. That'll be fun. Okay, well, let's call this region 1. Region 1 is x greater than 0, but not equal to 0. So x strictly greater than 0. So over here, this is region 1. But we have solved the problem in region 1. Now, there's a plus or minus here, and there are two constants, c plus or minus, right? But right away, I'm going to impose the condition. By the way, this just verifies what you said. You said that we expect the solution to be exponentially growing or decaying, and it is. Okay? It's growing if there's a plus sign. It's decaying if there's a minus sign. Does everybody see that? Okay? But we want y of plus infinity to be 0. And therefore, unambiguously, we know that this must be a minus sign. Yeah?
What if q tends to 0 at infinity?
We're going to assume that it doesn't. Okay? The problem is that then you have a turning point at infinity. Okay? And we want to solve only a one turning point problem. And a turning point at infinity is pretty fancy. That's a fancy problem. Okay? We can talk about that, but that gets too complicated right now.
We just have the same problem with a periodic potential.
You have the same problem?
With a periodic potential?
Yes. Yes, with a periodic potential, this is not trivial. Okay, so if the particle is in the periodic potential, this is not trivial. That's an infinite number of turning points. Okay? And then that leads to band theory. If you like, however, if we have time at the end, I'll show you a classical. I didn't show you the movie last time. We can look at a classical particle in a periodic potential, and that's fascinating. So I hope if we have some time, I'll show it to you. Show you what happens. Okay, pretty cool. But the periodic potential is particularly interesting because it involves new and really fascinating mathematics, and it involves the study of the Matthew equation and so on. This is a very important physical problem because that is the physics of a particle in a crystal. Okay, of an electron, for example, in a crystal, periodic potential. Okay. So far, so good, but what do we do at x is 0? That's the problem. Well, we begin by raising the blackboard, I guess. Let's see. Okay, so now, near 0, okay, so let's see. In some region about 0, like, for example, this region, which I'll call region 2, okay, so what do we do in region 2? In this region, when x is near 0, okay, what do I mean by x near 0 exactly? I mean x is small compared with 1. X is small compared with 1. Very small compared with 1. What do we mean by that? Well, I mean, what can we do when x is small compared with 1? Well, the only thing we can do is to do the method of dominant balance. Let's expand, let's take this differential equation and expand Q in a Taylor series. Okay, so that differential equation reads epsilon squared y prime prime equals, now the Taylor series for Q would have the form, say, the first term would be AX, right? That's the asymptotic approximation. Then there would be maybe bx squared plus cx cubed plus and so on times y. And what I'm going to do is the method of dominant balance. Okay? Near 0, this, all those guys are small. We will throw them away, and we will write down the following differential equation. Epsilon squared y double prime equals axy. That's the differential equation we're going to solve. Okay, now this is really, because we've thrown that away, this is an asymptotic differential equation. Okay, but let's study this differential equation. And in a moment, I will make it clear how the solution to this equation is an approximation to the solution of the exact equation. Let's look at this equation here. What equation is that? Well, let's see if we can reduce this to an equation that we know. Let's just do a scaling. Let's say, let x equal, say, I don't know, gamma, some number gamma times t, then this differential equation becomes epsilon squared over gamma squared, d squared dt squared y is equal to a gamma t y. Okay? And I would like to choose, let's multiply off, let's multiply by gamma squared. So what I would like to require is that a times gamma cubed over epsilon squared is 1. Okay? So if I multiply this by gamma squared, I get a gamma cubed here. If I divide by epsilon squared, I have an epsilon squared here. And I would like to require this to be 1. Why? Because I get a differential equation that I can look up in the books. So okay, so let's assume that this is true, so that gamma is equal to epsilon to the 2/3 over a to the 1/3. Okay? Do you all see what I'm doing here? Because if this is my choice of gamma, then this differential equation reads d squared y dt squared equals y times t. What? Yeah?
And this you have to somehow choose epsilon.
Yeah, epsilon is some number. Epsilon is some number for this argument.
But then you can't let epsilon at the end say go to.
Well, we're going to see how it works. You're going to see there are two. I understand your question. Your question is that epsilon is regarded as a small positive number, a parameter. Okay? And here, x is regarded as small. Okay, so we have two parameters in the problem, and we're going to have to organize what is the size of x compared with the size of epsilon. And we don't see that yet, so I'm being vague for a moment. You're going to see that happen. Yeah? No, a is a fixed number.
But
A is fixed.
I mean, like an infinite well?
Yes, then you have a separate problem. That would be an example where a is infinity would be a gravitational well. Okay, if you're bouncing a ball, the ball is absolutely not allowed to go through the floor. Okay, so in a gravitational well, just a bouncing ball, the potential would look like this. Okay, the gravitation. So x in this case is the height. That's the height. Okay, so the potential as the ball is bouncing, when it goes up, the potential rises linearly in a gravitational field. But at x equals 0, the potential becomes infinite. So a bouncing ball, so we're talking about the energy levels in this potential well. Okay? But we're assuming for now that a is a non-infinite number. Okay? And that's a different problem and an interesting problem, very interesting problem, if you would like to have a potential well like that. The way you solve the problem is that you don't say a is infinite, you say a is finite. This is a finite slope. Okay, but what you do is you impose the boundary condition that y of 0 is 0. That's how you impose this infinite wall. Okay, you just cut off the problem right there. You just say, I require that y of 0 to be 0. Okay, and then a is still finite, but the function v has a place where it's continuous but not differentiable at that point. So it's just you're only considered for positive x. Okay, all right. So this is the differential equation we have to solve. Ha! I know that differential equation. This is the area equation. Strange that I should have talked about it before in this course. Okay, this is the area equation. And the solutions to this equation, y of t, are called area functions. Okay, the general solution has the form some constant, call it d1 times ai of t plus d2 times bi of t. But I'm going to be a little bit intuitive here. You're going to see that what I'm saying is absolutely rigorous in a second. But we are looking for a solution which is decaying exponentially over here. In fact, we know how it's decaying. It's decaying like this WKB predicts. Now we know that the Airy function for large positive T is decaying exponentially. And we know that the Berry function is blowing up exponentially. And therefore, I'm going to say that this does not contain, this guy does not contain any Berry function, only an Airy function. And therefore, I'm going to look for a solution of the form y of t is some constant times ai of t. However, we could be completely general. Okay, and you're going to see in a second why this is a justified assumption. I mean, this is completely correct. Yeah, you have a question?
Yeah, I was just wondering, because like this solution was unique and from the ratio of two,
Of course.
but like we won't use like argument that we need the solution as infinity.
Oh, no. No. You're going to see in a second what's happening. You're going to see very soon what we're getting at. Okay? So I'm looking for a solution just now which has the character that as t increases, it decays. You're going to see how it works. Just hang on a bit. Okay, so this is the solution, but I don't want the solution in terms of t. We're looking for a solution in terms of x. So this becomes d times ai of, now what is t from this equation here? T is x over gamma, right? T is just x over gamma. So I have to write down x divided by gamma, which is a to the 1/3 over epsilon to the 2/3. And now we're beginning to see the answer to your question. Okay? Do you notice that there's an epsilon in the denominator? So for fixed x, and epsilon goes to 0, this argument becomes gigantic. And therefore, we know that the Airy function is exponentially decaying. If there were a Berry function, it would be growing very fast. In the limit as for small but fixed x, and epsilon goes to 0. I'm going to make that clearer in just a second. Okay, but let's summarize what we've done. We have said, to be precise, we have said that y of t is asymptotic to this in region 2, this function. And y of t is asymptotic to this function in region 1. Here's region 2, here's region 1. Now, even if we were in 3rd grade, if I said to you, please look up at the board, we are only solving one problem. And there's only one solution to this problem. This is the problem we're solving. And we've written down the solution here, and we've written down the solution here, and they don't look anything like each other. Now, we claim that in region 1, the solution looks like an exponential of an integral divided by q to the 1/4. In region 2, we claim the solution looks like an Airy function. Okay, it's given by Airy function as an asymptotic approximation, but it's got to be the same solution if the two regions overlap. So I want you to notice right here, I've drawn this in a very suggestive way. Right over here is an overlap. And in this overlap region, these two solutions should be the same. But they're not the same. They don't look the same. So what we're going to do is amazing. What we're going to do is we're going to construct an asymptotic approximation to an asymptotic approximation, which is valid in the overlap region. Now let me say this again. This is valid, this here is valid everywhere, everywhere, and I emphasize everywhere in region 1. That's valid everywhere in region 1. This is valid everywhere this guy here is valid. This approximation is valid everywhere in region 2. For example, it's valid at the origin, where x is equal to 0. It's valid everywhere. But I'm going to make a further asymptotic approximation in the overlap region. Okay? Now, how do we do this? So we have to define the overlap region. Where is the overlap region? In fact, we need to go and get a book. We need to look up the asymptotic behavior of the Airy function, because we're going to make a further asymptotic approximation to this asymptotic approximation. Okay? And in a book, we can see that AI of x, let's call it something else. AI of s is asymptotic to e to the minus 2/3 s to the 3/2 over s to the 1/4 power times 1 over 2 square root of pi. And the one thing that we have not derived in this class or explained is where that number comes from. Okay, but that is a normalization constant. Okay, this is valid as s goes to plus infinity. So this we look up in a book, and we find out that that is true. Okay, and you've seen this result. We've talked about this in class. Okay? When can I make the replacement that this Airy function is given by this asymptotic approximation? I can make that assumption if x times, or a is a constant, you understand. A is just a fixed number like 21 or something. But so long as x over epsilon to the 2/3 is large compared with 1, then I can approximate the Airy function using that formula. Do you all see that? Right? That means so long as x is large compared with epsilon to the 2/3. Now, that means that x doesn't have to be very large, right? It doesn't have to be very large because epsilon is very small, but could x be 0? No, it can't. Okay? It cannot be 0. It has to be large compared with epsilon to the 2/3 as epsilon goes to 0. So, where is that on our plot? Let's put this. So I say that the overlap region begins down here around, this is the point here, around epsilon to the 2/3 power. So as soon as x gets bigger than epsilon to the 2/3, I am in this overlap region here where I can make an asymptotic approximation to my asymptotic approximation. Okay? If I do that, I'm going to use that formula, and I'm going to conclude that in the overlap, in the overlap region where this is true, where this defined by x being large compared with epsilon to the 2/3, that means this argument of the Airy function is big, and I can replace this formula by y is asymptotic to d times 1 over 2 square root of pi, right? Just using that formula, times e to the minus 2/3 times this argument to the 3/2 power, which is x to the 3/2. What's a to the 3/2? Square root of a. What's epsilon to the 2/3 to the 3/2? Epsilon. Okay. Epsilon. Okay, and then it's divided by the argument to the 1/4 power. And what is the argument to the 1/4 power? It would be x to the 1/4. What's a to the 1/3 to the 1/4? A to the 1/12. What's epsilon to the 2/3 to the 1/4? 1/6. Okay. Epsilon to the 1/6. So in the overlap region, we approximate this asymptotic approximation by this asymptotic approximation. Okay. Are you with me? Are you following this? Let's go back to the WKB approximation. This is valid everywhere, everywhere in region 2. That is, starting somewhere above 0 and running all the way off to infinity. But suppose we look in the overlap region. In the overlap region, x is small compared with 1. If x is small compared with 1, now let's go down here. You notice I left this integral and the lower end point of the integral ambiguous. What would you take it to be? What's the one interesting point in this problem? 0. So therefore, let's take this to be 0. If it's something else, all we do is we adjust the multiplicative constant, right? It just multiplies it. So without any loss of generality, I'll take it to be 0. But if x is small compared with 1, what can we say? We say that if x is small compared with 1, we could replace everything in this integral by the Taylor expansion of the integrand. What would, and also we can replace q by its Taylor expansion. So in other words, that y of x can be further approximated, say, as follows. We have in the denominator q to the 1/4. And that would be ax plus bx squared plus and so on, all to the 1/4 power. You see? You all with me? And up here in the exponent, we have e to the minus 1 over epsilon, integral from 0 to x dt. And in place of q of t, I write the square root of at plus bt squared, and so on. Now, if x is small compared with 1, I'm going to throw away those terms in the Taylor series in my asymptotic approximation. Now, I'm not sure about whether we can throw away all the terms in these series. Let's be careful. Let's be careful here. This is c over a to the 1/4 x to the 1/4. Okay? But over here in the exponential, I have e to the 1 over epsilon, integral from 0 to x dt. Now, let's just let's just approximate this for small t, So what I get, I can factor out a square root of at, and then I'm left with the square root of 1 plus bt over a, right? And this I can expand in a binomial series as 1 plus bt over 2a. And if I multiply this out, I have an integral from 0 to x dt. The first term is the square root of at. That square, let's write it as the square root of a times t to the 1/2. And the next term will be b over the square root of a times t to the 3/2 plus more terms. Okay? And now I'm going to do the integral. So this integral gives me square root of a times 2/3 t to the 3/2. Yeah. Factor of 2. Thank you. Okay. You're not asleep. I can tell. Okay. Excellent. Now, the next piece is b over, and there's your 2 times the square root of a. And the integral of t to the 3/2 is t to the 5/2 times 2/5. We didn't need your 2. They cancel. Okay, see? Okay, and now we evaluate it at the endpoints. And when I evaluate it at the endpoints, I get c over a to the 1/4 x to the 1/4 e to the minus 1 over epsilon times, now, look at this, 2/3 square root of a x to the 3/2. And the next term is b over 5 square root of a times x to the 5/2. And plus more terms. Okay, I did the integral. Right. Now, what I would like to do, what I really, really like to do, is to throw that term away. In order to throw this term away, I need to require that, we need a little more room. Okay, in order to throw that term away, what do I have to require? I have to require that x to the 5/2 power over epsilon is small compared with 1. I would have to require that. Okay? And that's only true if x, that tells me that x to the 5/2 is small compared with epsilon. Right? It can't be too big. Okay? Or that means that x is small compared with epsilon to the 2/5. Whoa, wait a minute. We just said that in the overlap region, x has to be large compared with epsilon to the 2/3. Can we be large compared with epsilon to the 2/3, but small compared with epsilon to the 2/5? I mean, to this here, is that true? Small compared with epsilon to the 2? Is that possible? Maybe that's ruled out. Which is bigger, epsilon to the 2/3 or epsilon to the 2/5? Epsilon to the 2/5 is almost epsilon to the 0, right? Which is 1. Epsilon to the 2/5 is closer to 0 than 2/3, right? Therefore, epsilon, a smaller number to the 2/5, that's getting close to 1, right? In fact, the order of this, now you're seeing the way this works. Let's move this all the way down. At the lower end of the overlap region, we have epsilon to the 2/3. But at the upper end of the overlap region, we have epsilon to the 2/5. You see that? This is so delicate. The key thing is that epsilon is going to 0. If it's going to 0, this is much smaller than that. Okay, there's an infinite amount of size. The ratio of this to this is infinity. Therefore, we have a huge overlap region. 1, of course, is all the way up here. That's 1. So the Airy function approximation is valid all the way up to 1. That's region 2. The WKB approximation is valid all the way from here, all the way up to infinity. And we have an overlap. And the overlap is those x's that are large compared with epsilon to the 2/3, but small compared with epsilon to the 2/5. This, I'm not nitpicking here. This is absolutely crucial. Okay? But if we assume that, that's the case, if x is small compared with epsilon to the 2/5, what can we say? We can say that this term can be thrown away. And that means that the WKB, y, which is asymptotic to y WKB, is asymptotic to a much simpler approximation. We have done an asymptotic approximation to the WKB asymptotic approximation. An asymptotic approximation to an asymptotic approximation. Okay? And the formula reads now c over a to the 1/4 x to the 1/4 e to the minus 1 over epsilon times 2/3 square root of a x to the 3/2. Now, we look at this result over here, and we look at this result over here. I want you to see that it is exactly the same function. Okay? So in the overlap region, there is only one function. And now this is the answer to the question that I think you asked me early on. Why can we throw away that BI function, the Berry function? That's because the only change would be that there would be an e to the plus da-da-da-da. And at this point, we would conclude that the coefficient of that function must be 0. Okay? Because these two functions have to be the same in the overlap region. This is not patching. When you took an elementary course in differential equations, you patch the two solutions together. When you solve the square well in quantum mechanics or wells like this, you patch the solutions at a point. We're not doing that. We are doing something phenomenally beautiful. This is called asymptotic matching. We have a matched pair of asymptotic approximations. We have matched this asymptotic approximation in region 1 to this asymptotic approximation in region 2. Yeah?
I just have trouble with the fact that we, at the end, want epsilon to go to 0.
Yes.
And
this is only valid and the limit as epsilon goes to 0.
But
And now we know the range of x that we have to work in given that epsilon is going to 0.
But for these two functions to be equal, d has to be
They're not equal.
at
They're only asymptotic.
D
Definitely
has to
not
go
equal.
like epsilon.
Sorry?
D has to go like a function of epsilon. Cancel.
D?
Yeah.
Oh, sure. D is going to depend on epsilon. That's right. There's nothing wrong with that. We haven't said anything about D yet. We're going to find the relationship between C and D. And indeed, there is an epsilon in here, right there. That's right. We are treating D as a constant, as a function of x, as a function of x. Okay? We are saying that this function of x is the same as that function of x. but its epsilon dependence is going to be very, very complicated. Okay, well, not very complicated, but it's going to depend on epsilon. Okay, so these are the same function if, now I want you to notice there is a 1 over epsilon 2/3 square root of a x to the 3/2. That exponential is exactly the same as that exponential. And there's an x to the 1/4 here, and there's an x to the 1/4 here. But these are only asymptotic if the constants multiplying these two identical functions of x agree. And that means that c over a to the 1/4, all this implies that c over a to the 1/4 must be equal to. Now you notice this is an asymptotic relation. But the only way this guy could be asymptotic to this guy, this guy to this guy, is that the ratio be 1. And the only way for the ratio to be 1 is for the multiplicative constants to be equal. So from an asymptotic approximation, I am deducing an equality. That's not the way we usually go. Usually, we start with an equality and replace it by an asymptotic approximation. But now I conclude that two constants are equal. The constant c over a to the 1/4 here, and the constant d over 2 square root of pi times epsilon to the 1/6 over a to the 1/12. Okay, those are the multiplicative constants. That has to be an equality. And if that's an equality, we conclude that, well, we can simplify this a little bit. What is 1/4? 1/4 is 3/12. Right? And if I subtract 1/12 from 3/12, I get 2/12, which is 1/6. Okay, so this is a to the 1/6. So if I solve for d, for example, I get d is equal to 2 times the square root of pi times a epsilon to the minus 1/6 times c. All right, here's an a to the minus 1/6, an epsilon to the minus 1/6. That is my conclusion. Okay? Yeah. Certainly not. In fact, so if it doesn't work, we're up a creek. If it doesn't work, we're up a creek. The reason that it worked is that an overlap region existed. Okay, so we did one asymptotic approximation here, one asymptotic approximation here, and there was an overlap. If we did an asymptotic approximation, it was only valid up to here. And the second asymptotic approximation was valid from here on. There would not be an overlap, and these two functions would not look the same. There would be no way to make them the same, so then we would look for a third asymptotic approximation that's valid here. And we would then match over here and over here. If you're very intuitive, you can see it. That's key, absolutely key. This fact, so what, again, so let me emphasize what you just said. What is the overlap region? What is the precise statement of the overlap region? The overlap region exists, and in fact, what is it? It's all x that are huge compared with epsilon to the 2/3, meaning that the ratio of x over epsilon to the 2/3 is going to infinity, but negligible compared with epsilon to the 2/5. That is the overlap region, and this is an asymptotic statement, and this is valid as epsilon goes to 0. And the fact that that exists is why we can do WKB. Okay? This is really a tour de force, right? Do you agree? This is really fantastic. And it's very subtle. You will never learn this in an elementary course on quantum mechanics, because no one's ever going to work this through. Okay. But we're almost done now. because now we have the relationship between D and C. And now I'm just going to fill in the end. Okay, we're almost there. Here's the answer. Here's the answer to our problem. We can write it down. In region 1, region 1, what can we say in region 1? Y of x is asymptotic to a constant which we cannot determine. Okay, this is a linear differential equation, so we don't know what the constant is, times 1 over q of x to the 1/4 times e to the minus 2/3 epsilon to the 3/2. Oh, sorry. E to the minus 1 over epsilon, copying this down, 1 over epsilon times the integral from 0 to x dt square root of q of t. That is how this is an asymptotic approximation which is valid everywhere in region 1 in the limit as epsilon goes to 0. What can you say about region 2? Region 2, y of x is asymptotic to d, which is this, which is 2 square root of pi divided by a epsilon to the 1/6, right here, times this constant c, okay, times an Airy function. And the argument of the Airy function is x times a to the 1/3 over epsilon to the 2/3. X times a to the 1/3 over epsilon to the 2/3. Okay? As epsilon goes to 0, but we don't care about that. What we really care, if we ask where is this valid, it's valid so long as x is small compared with 1. This is valid so long as x is greater than 0 and epsilon is going to 0. This is valid so long as x is small compared with 1. Okay, for fixed epsilon. And that's everywhere in region 2. Now, I'm not going to do the calculation for you because I don't want to bore you to tears, but there's only one more fact that you need to know. If you look up in a book, what does AI of S look like as S goes to minus infinity? It doesn't look like this, because I talked to you a little bit about the Stokes phenomenon. There's a different asymptotic approximation, and in that region, the Airy function is oscillatory, and AI of S looks like 1 over the square root of pi, not 1 over 2 square root of pi, but just 1 over square root of pi, 1 over square root of pi, times 1 over minus s to the 1/4, okay, because s is going to minus infinity. We want to deal with a positive quantity here. And then there is a sine of 2/3 minus s to the 3/2 plus pi over 4. Okay, so in general, it's a linear combination of sines and cosines, but if I put in this phase, this is how it behaves. Okay? If we then do WKB and match it, we just repeat the process that I just explained to you, we could take another half an hour and write the formulas on the board, but let me show you what the answer comes out to be. In region 3, which is x less than 0, that's the region. What does the WKB approximation give? Y of x is asymptotic to 2c, not c, but 2c. Not c, but 2c. The reason for the 2 is because here there's a 2 in the Airy function approximation, but there isn't a 2 here. Okay? So we match the WKB solution to the airy solution. So there's another matching region on the left-hand side. Okay? So we have region 1, a matching region going to region 2, another matching region going to region 3, which is x less than 0. Here's x greater than 0. And what the solution looks like is over minus q to the 1/4 sine of 1 over epsilon, okay, integral from x up to 0, because I want x is negative here, and I want everything to be positive. So I'm writing down minus q here. I'm integrating in the positive direction from x all the way up to 0, dt square root of minus q of t. I'm writing minus q because q is negative here, plus pi over 4. This is a great, great breakthrough of the 20th century. This is the solution to the one turning point problem. We have solved a Schrödinger equation where there is a turning point present. How did we do it? We did WKB, and just before the WKB broke down, we matched the WKB to an Airy function. And then just before the Airy function was no longer valid, because x was getting significant compared with 1, not negligible compared with 1, the WKB solution takes over again, but you can see that the WKB solution here is oscillatory. Here it is wave-like, and therefore we are in a classically allowed region where the potential is less than the energy. Here we're in a transition region, in the turning point region. Here we're in a classically forbidden region where the probability of finding the particle is exponentially small. That's it. Boy, would I wish to have done this. I mean, I've done lots of matched asymptotic approximations, of course, in my life, but this is just aces. Is that fantastic? Okay, now I want to show you how good it is. Okay? How good is this approximation? I mean, is it this good? Let's see. Now, by the way, before we go on, you understand what I've done. I have not done local analysis. I have told you what the solution looks like for all x. Okay, this is not just valid for x being near plus infinity or near 0 or something like that. This is valid for all x. We have covered the entire line from minus infinity to plus infinity. There it is. Okay, so let's see how good it is. Okay, so what I did was to take some function q, okay, and this is the, I mean, I tried to be as silly as possible, okay. So I said, let's take q of x to be sinh of x times cosh squared of x. Okay, and I hope you agree that sinh of x times cosh squared of x vanishes at x equals 0 because sinh of 0 is 0, right? And it only passes through 0 once. So this satisfies the condition of our problem. And I impose the condition that y of 0 is 1. How would you require that y of 0 be 1? Of course, I impose the condition that y of infinity is 0, but I'm also saying y of 0 is 1. How do you impose that condition? Well, you go to region 2, because that's where x equals 0 is located. You say you have to look up the value of ai of 0. So if you look up in a book, I don't remember what it is, but it's, it's gamma of 2/3 over 3 halves to the 1/3, something, some number, okay? It's some number. We don't care what it is. You plug it in here, and that tells you what c is. That fixes the overall constant. So this is an equation for c. So 1 becomes equal to 2 squared root of pi over blibbity blah, 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 blah. It's a formula for C. Okay? So I plotted it. And here is the exact solution. And here is the WKB approximation that we derived. Okay? When you make a plot of it, I mean, I hope you're impressed. Now, this is epsilon equals 0.2. This is only valid as epsilon goes to 0, but here's epsilon equals 0.2. You notice the solution is oscillatory over here. That's the classically allowed region where particles are wave-like. This is the classically forbidden region where the probability of finding a particle is going down exponentially fast. And the agreement is almost precise. I can see a little error over here, and a little error over here, and a little error over here. But apart from that, this is pretty damn good. Okay? So this is uniformly valid. Yeah?
How do you go about plotting something that you have? Yeah, that's included.
I knew you'd ask me. So I will tell you a little bit about that. I'll tell you a little bit about it. Let me just give you a brief answer. Okay? You notice there are 3 different formulas. But in fact, you can combine this into one single formula called a uniform asymptotic approximation. Okay? Which in this region reduces to this, and in this region reduces to this, and in this region reduces to that. Okay? And that was discovered originally back in the 1930s by a guy named Langer, okay, and in 1932, okay. And this is Langer's formula, and that's what I'm actually plotting. However, you can't see the difference. If you make a plot, somewhere between this and this, you change over, instead of plotting this function, you start plotting that function. Okay, and then again, when x is negative, somewhere in the middle of this for negative x, you stop plotting this and you start plotting that. You can't see where it makes a jump. Okay, just microscopic. Okay, and that's how the formula comes out. Okay.
This is where you can see a kink.
A kink. A kink? Oh, you mean this? Oh, right here? Oh, yeah, there's a, I think that, unfortunately, that's not real. That's a Fig Newton, okay, that comes from, you know, it's just there's so many pixels in the plot, and it just jumps, okay? That is not, I see what you're saying. That thing right there is not there. That's just a computer thing having to do with the size of the pixel. Okay, but what if we make epsilon bigger? It must get worse, right? So let's take a look. Here is epsilon is 0.3, and you can see that the disagreement is getting a little bit bigger. Okay, and here's epsilon 0.5. Okay, and it's getting a little bit bigger. Let's take epsilon even bigger, say 0.1. That's pretty darn good. But you can see that the error, there's now a visible error here. So there's some error over here, and there's some error over here. But it is good because as you go off toward infinity, the 2 lines are again overlapping. And as you go off toward minus infinity, they are getting closer and closer and closer, and you will no longer be able to see the difference once you're below about here. Okay? This is really impressive. Okay, you had a question. Yeah, epsilon, again, in region 3, this is valid as epsilon goes to 0. I didn't write it down, but it's as epsilon goes to 0. Why is it true? Because the WKB becomes valid as epsilon goes to 0. That is the condition for this symbol being used. Okay, and of course, what we have done, when we say that it's valid as epsilon goes to 0, you understand the error would be, can you see? The error is 1 plus epsilon S2. So we're saying that to justify this being valid, we are throwing away that term. Okay, that's the assumption that we're making, that we can neglect, the correction would be epsilon S2. Of course, if you wanted to be more accurate, if you wanted to get a better approximation, you don't throw it away. You keep epsilon S2, and you throw away epsilon S3. And if you want even better, you keep epsilon S3, epsilon squared S3, and epsilon cubed S4, et cetera, and you get a better and better and better approximation for small epsilon. S2 is not small, but epsilon S2 is small. Because X is getting pretty big. And WKB is also very accurate when X is big. So when epsilon is not terribly small, X is still getting big, and because X is getting big, WKB is very accurate. Okay? I mean, there are two ways of making this thing up here big. One way is to multiply it by 1 over epsilon. The other way is for X to fix epsilon and let X be big. Okay? Because this is a big function, sinh times cosh squared. So it's pretty nice. Okay? So this is fantastic. But we haven't yet finished the problem yet. We haven't. Yeah, you have a question?
If you want higher terms, would you be matching up all of them separately, or?
You have to do the following. If you're going to include epsilon S2 here, if you're going to include that correction, then in order to get an asymptotic match, you need the next term in this asymptotic series for the Airy function as well. Okay? And this is not the entire asymptotic approximation to the Airy function. It's multiplied by 1 plus, or it's actually minus, I think, 5 over 48 s to the 3 halves times, and so on. Okay, this is a series. Okay, and that indeed is going to match with this term here. Yeah, oh yeah, and that's because, to all orders, and that's because the overlap region exists. If it exists, it exists. There's only one solution to one differential equation. So this representation of the solution in region 1 and this representation in region 2 have to become the same representation in the overlap. No other conditions. They have to agree term by term, and they do, which is fantastic. You really have to agree. This is a phenomenal calculation. Order by order. This is not just, I just showed you the leading order, but order by order, it has to work. Yeah?
What happens to the overlap region?
Oh, remember the overlap region has only an asymptotic existence. It exists in the limit as epsilon goes to 0. Once we pick epsilon, once we say, let's take epsilon equals 0.5, then you can no longer talk about an overlap region. Okay, if epsilon has a numerical value, then statements like this are meaningless. So you just have to hope that the final answer is accurate. But
how would you mash up then if you were to plot it somehow?
You can't match for a fixed epsilon. If you say epsilon equals 0.047 or something, you can't match, because then this is not an asymptotic relation. That would become an inequality of some sort, which is nonsense. Okay, so this is only an asymptotic calculation. We only check the numerics at the end of the calculation, and we have no justification for assuming that this is going to be this accurate when epsilon equals, if you just say at the end of the calculation, let's choose epsilon equals 1.
No, but after you've calculated and you want to plot it for some epsilon.
Yeah. Yeah.
I mean, you're plotting the three regions and somehow matching them or using the uniform.
Right, right. If you use the uniform asymptotic approximation, then there's only one function, only one formula. We just plot it from 0.
But there is no region 2 in that case. If you
That's
said-
right. It's very hard to define. Okay, so you choose, you try to choose. If you didn't know Langer's approximation, you would say, well, what is this numerically equal to, and what's this? And the changeover from region 1 to region 2 is somewhere halfway in between or something. There would be some artistic decision on your part. Okay? What I want to say here is this is a great, great triumph of the 20th century, because look what we've done. We have actually seen a transition from the classically forbidden region to the classically allowed region. There's a turning point at x equals 0, and we see the particle going from being, the wave function of the particle going from being exponentially small to becoming oscillatory. In the classically allowed region, a particle is a wave, and it's wave-like, it's oscillatory. Okay? We see it. This is quantum mechanics working right in front of your eyes. You can see that. But next time, this was a pretty long calculation. Next time, I'm going to do an unbelievably brief calculation. And all I'm going to do is, I'm going to take the one turning point solution here and the one turning point solution here, right? We figured out the one turning point solution. And what I'm going to say is, look, there's an overlap region. Where is the overlap? It's in the classically allowed region. And we're going to put them together. And when we do that, what we have to do is require that the waves that are coming off here and the waves that are coming off here are the same waves. We have to line up the waves. And when we do that, we're going to see quantization. That's where quantization comes from. That's how you can understand quantization. Okay? And from that, we're going to calculate the energy. We're going to actually figure out what the energy really is. That's utterly amazing. Okay? So, any further questions? Or, yeah, Tibor.
So in this case, we don't really know what the eigenvalues are, right?
No. Oh, no, no, no. At this point, in fact, in this part of the calculation, I never use the word E, the letter E, unless I said the word onomatopoeia, because that contains the letter E. But did I? I don't remember saying that. Okay. Okay. Or Callipygian. Yeah, that has an E. Yeah. And I didn't say that. Okay. So E doesn't appear in here. As far as E is concerned, E is buried in the function Q. And Q is just some fixed function. Okay? So it doesn't matter what E is at this point. Okay? And tomorrow, what we're going to find is that if we demand that one turning point solution match to the other one turning point solution, to form, we're going to glue them together to form a two turning point solution, it cannot in general be done for arbitrary functions Q. Can't be done. There's no reason that you can do it. There's no reason that these waves should line up. The wave coming from the right, will be going like this. The wave from the left will be going like this. And they're not the same wave. Unless Q is very special. And that's called quantization. And that's where the quantization comes from. So at this point, we have no quantization. We just solved the Schrodinger equation. Yeah?
I guess you got the exact solution numerically?
Yes. Oh, yes, yes. And to get the exact solution numerically, you know what I did. I took a large value of x and integrated down towards 0 and kept going. Okay. Just kept integrating until I got tired. I got tired at -2. Okay. But I could have kept going. Just constantly. Okay, any further questions? Okay? I hope you're impressed. This is fabulous stuff. I mean, this was essentially, this is one of the prominent breakthroughs of the first half of the 20th century. Because you understand, these famous smart guys, like Pauli and, wrote down the Schrodinger equation. Even Schrodinger wrote down the Schrodinger equation. In fact, afterward, by the way,